Hey, kids, we're going to do face homework number 3, the first page first. This is about drawing a cooling curve for bromine. All right. All cooling curves look pretty much the same. Look, I cheated and put BR here so I remember what it is. For a title, we're making, it says a cooling curve. So the title is going to be Cooling Curve for Bromine. And we're going to have temperature on the y-axis, and we're going to remove heat at a constant rate. So down here would be time 0, and here would be 0 Kelvin, exclamation point, because we never go to 0. Now on a cooling curve, we're going to start really, really hot and work our way down, right? Because it's going to get cooler over time. So I cheated. I looked up right here on table S. Bromine is right here, and these two temperatures, the melting point and the boiling point for bromine, I wrote them down so I'd have them available. The cold temperature is going to be 266 Kelvin, and the hot temperature is going to be 332 Kelvin. Now this is the boiling point, right? The boiling point, but that also is equal to the condensation point, and on a cooling curve, we're not having any boiling. This is the melting point, but of course this is also the freezing point, and on a cooling curve we're going to freeze. So we're going to need to condense and we're going to need to freeze. Now it's got to start higher than this. Anywhere, pick a point right here. That's my starting point, A. Now as I remove energy, the temperature is going to go down until I get to the condensing point. At that temperature, the temperature stays flat for a pretty long time. And then, because it's cooling curve and I'm removing energy, the temperature is going to go down, down, down until I get equal to the condensing point, or in this case, the freezing point. It's going to stay flat for a little while, and then it's going to go down again. I'll put a point in here and an arrow. Now I'm going to label this A, B, C, D, E, and F. Now, we don't have to do anything else to this graph, but I'm going to write some stuff in to remind myself. Here, it's a gas. Here, it's a gas, and it's going to become a liquid there. C is a liquid, LIQ, and it's going to stay a liquid all the way to D. This is the liquid cooling, cooling, cooling. This is where it's going to go from liquid to solid, and down here it's only in the solid phase. And you could make it as cold as you want, but you can never go to absolute 0. Now, what phase or phases is from A to B? Gas only. What about B to C? We have gas turning into a liquid. What about from C to D? We have liquid only. And what about, here we got to move up from D to E. This is liquid to solid, and then we have just solid from E to F. Now, what's happening to the kinetic energy and temperature? Now, these two work hand in hand. From A to B, the temperature is going down. Look, it goes from whatever this temperature is down to there. So if the temperature is decreasing, the kinetic energy decreases as well. Now, since one energy is changing, this is steady. We don't need to have any potential energy change because we're not changing phases. Now, in BC, we are changing phases. BC, the temperature is 332 and it stays 332. So in this case, the temperature is steady. That means the kinetic energy is steady, but the potential drops because gases have a higher kinetic energy and liquids have a lower kinetic energy. So even though it's the same temperature, the potential dropped. From C to D, we start out with liquid, we end up with liquid, but the temperature is surely going down, and the kinetic energy does the same thing because the kinetic energy and the temperature always do the same thing. And since there's a change in kinetic energy, that means there's going to be steady potential energy. Now, this D to E business, this short one, this is actually the freezing point. It's going to freeze right across here. It's liquid, and it's going to become a solid. So when we look at D to E, the temperature stays steady, and that means the kinetic energy stays steady. But it's going to decrease the potential energy because it's going from a liquid to a solid, and solids have a lower potential energy than does the liquid. The final section down here, it's a solid and it stays solid, but the temperature is definitely going down. That means the kinetic energy is going down, and this means that's steady as well. So there's that little table. This is a cooling curve. Now, for the second page of homework number 3, here's homework number 3, page 2. First off, there's a boo-boo. You got to change this. This is going to be a heating curve, but I copy and pasted and forgot to change it. So we're going to add heat. Minor. Now, this says heating curve for phosphorus. I cheated and wrote phosphorus right there. I already have the title, heating curve for phosphorus. And look, over here I cheated too. Phosphorus is element number 15, and the numbers are 317 and 554. The melting point and the boiling point for phosphorus. So on a heating curve for phosphorus, we have two temperatures, hot and cold. Down here is 0 Kelvin, exclamation point, because we never do that. And this would be, of course, time 0. Time 0. And then time just goes forward. So we need to, for phosphorus, put these two temperatures in. This will be 317 Kelvin. That will be the melting point. And 554 Kelvin from table S, that tells us the boiling point. Now, on a heating curve, we start really, really cold, and we go up. Now, how cold can we start? We can't start there. We have to start above absolute 0, and I'll call that point A. Now, the temperature, when we add heat, is going to go up, up, up until we get to that special temperature called the melting point. Then there's going to be a step. There's B and C. And then, once it's already melted and turned into a liquid, this temperature is going to go up, 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 all the way to the boiling point at D. And then we're going to have a long section to E, and then it's going to go up. Here's point F, and we'll give that an arrow. It can be as hot as you can make it. If you send it to the sun, it could be 1,000,000 Kelvin. Now, what's going on? This, of course, is the melting point. So below the melting point makes this a solid only. Across here, it's going from the solid to the liquid phase. In the middle, it's liquid, and it stays a liquid all the way up to the boiling point. In a boiling point, things go from liquid to gases. And then above the boiling point, it's only going to be in the gas phase. Now, you don't have to do that, but that I think is helpful. So what's going to happen at these particular segments? From A to B, let's see, that's down here, A to B, that's going to be only a solid, only. The temperature is surely going up, and that means the kinetic energy goes up because these two always do the same thing. And since kinetic energy goes up, the potential energy is steady because only one energy changes at a time. From B to C, we're having a phase change from solid to liquid. This is called the melting point. It's going to melt. So we have solid to liquid, but the temperature is steady. It stays at 317 Kelvin, 317 Kelvin, 317 Kelvin, still 317 Kelvin. The temperature is steady. That makes the kinetic energy steady, But the potential, because we're going from solid to liquid, the potential energy increases, exclamation point. CD, right through the middle. Liquid, 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 but the temperature's going up. So what do we got? What phase? Liquid only. The temperature is definitely increasing. That means kinetic energy is increasing. The particles are moving faster and faster. What does the potential energy do? It stays steady because only one energy at a time can change. And if the kinetic energy is increasing, then the potential has to be steady. Now, DE, cross here, phase change from liquid to gas at the boiling point, 554 Kelvin, steady as she goes. So what phase do we have? Liquid to gas, it's a phase change. The temperature is steady, and the kinetic energy is steady because they do the same thing. No change in temperature, but the potential increases. I'll give you another exclamation point because we're going from liquid to gas, and gases have a higher potential energy. Last section, EF, that's over here. We have gas only. The temperature is surely increasing, and that means the kinetic energy goes up because whatever the temperature does, the kinetic energy does also. But since only one energy can change at a time, if kinetic energy is increasing, that means this is going to be steady as she goes. There you go. My phone's ringing and we're done at the homework at the same time. Great.